With more and more embedded systems requiring RF integration, the ability to debug and time correlate embedded in RF signals is critical. Using the RSA and 7000 series oscilloscope together, we can analyze, capture, and isolate these signals, including short duration pulses, being able to navigate and analyze through signals of interest on our oscilloscope, and combining time correlated data with our other embedded signals. Let's look at how we do this. First, we connect a couple of connections between the scope and the analyzer on the rear of the instruments. The trigger output from the analyzer to the external trigger on the oscilloscope, this oscilloscope's trigger output into the trigger input on the analyzer, and then we use, most importantly, the RF output of the analyzer, which gives us a look at the real-time bandwidth brought down to a 430 megahertz carrier into a channel on the oscilloscope. That gives us the ability to really look at those RF signals and time correlate them with other embedded channels. We could use the channel offset timing capabilities of the oscilloscope to get rid of any sort of timing latency and correlate our signals perfectly. In this multi-domain application, we're using the 7000 series, triggering on an RF pulse, to analyze and time correlate that RF pulse with our embedded signals. Here we can see that pulse is about 1.5 microseconds. So we're really able to characterize the frequency of that because of the high sample rate of this oscilloscope. We can see the Keller FFT across the top using the deep memory to capture that frequency and bucket it. We can see how it fits in 7 channels of FSK data. We can then time correlate those pulses with other embedded signals like the digital logic channels we see at the bottom of the screen. Altogether, the enhanced Keller FFT combined with the high sample rate and deep memory make the 7000 a great instrument for these sort of multi-domain time correlation applications. One of the advanced ways we can look at sequence of pulses using the deep memory 7000 series oscilloscope is to use record mode. Here what we can do is we're still capturing series of these pulses, and we can see the frequency moving around. And we also have different pulse types. Like we talked about, we have some good pulses and some pulses that have gaps in the center. So how do we look at the sequence of events there? Well, one way is we can use the record mode capabilities within this scope. And this will let you record really thousands of frames of activity. So each pulse is being triggered, is causing a frame. We're capturing those frames and really using the sequenced and the segmented memory here to do further analysis. So whenever we feel like we have enough there, we can go ahead and stop that activity. And then we can play it back either as a movie, or we can go ahead and look through sequences of frames, and we can see, now we can go and look and say, all right, each bad pulse or double pulse, what's causing that activity, what frequency is that at, what's the pulse sequence and timing, and see how that all works together. Many multi-domain applications require capturing and isolating high-frequency RF signals and combining them with your embedded signals. With the RSA 5000, we can capture up to 6.5 gigahertz signals and then use the frequency mask trigger, like we are here. The green shaded area only captures RF pulses, RF signals within that piece of spectrum. From there, we can trigger out to the oscilloscope. Let's see what that looks like. So now on the oscilloscope, we can see the RF pulse. It's generating that frequency in the center on channel 1. We can see the FFT of that, so we can see the frequency as well. Now we can time correlate that pulse activity with the logic channels at the bottom of the screen or other analog channels. That really makes it possible for us to then time correlate, find root cause of any issues, and do complete embedded debug with both our embedded signals and RF signals up to 6.5 gigahertz.